Okay, I will start. Am I audible to all? Please put it in chat box. Otherwise, unmute yourself. Okay. PPTs are visible. Okay. Shall I start? Thank you. Okay, in yesterday's lecture, we have seen the basics concepts of the processing unit. In that, we have seen the basic blocks of the processing and functional units of the processing unit. Each blocks which is involved in the processing unit, we are seen in detail. Now, we are going to see in this lecture processing units types. In central processing units, there are mainly two types. First one is hardware control unit. Second one is microprogram control unit. Out of that, in this lecture, we are going to see hardware control unit. Now, this diagram represent the hardware control unit. In this hardware control unit, first thing is that the number of blocks which is involved in the hardware control unit, which will be controlled by the hardware only. And in microprogram control unit, it will be controlled by the microprogram control unit. That is the difference between the hardware control unit and microprogram control unit. Now, first block is instruction register. Here, instruction registers, instruction register will be input is given to the instruction decoder. Instructions are decoded, and after decoding, it will be given to the control signal generator. Here, instruction decoder, there are n number of lines are given. That is INS 1 to INS n. These are the lines which is given. This instruction decoder capacity is depending upon the number of data lines available in that particular processor. For example, if it is having the 8 lines, for example, if it is having the 8 lines, so 8 lines are there in the instruction decoder. So total 2 raised to 8. That means 256 lines are generated from this instruction decoder to the control logic generator. So that many lines are sent to the control logic generator. Out of this, as this control logic generator is taking at a time only one line. So for example, if I'm saying that the INS1 line is active, that means it is having value 1 and remaining all. For example, in case of 2 raised to 8, 256 line, out of that only one line is activated, remaining lines are not activated. That means all these lines INS2 to INSN, all these lines are having value 0. That means at a time only one control signal is generated from instruction decoder and it will be provided to the control logic generator. Then we moving to the next part. Whenever we are using this control signal generator, it is a combinational circuit. So it is going to generate the required control output for the decoding and encoding functionality of the hardware control unit. Now, if you see this control logic block, this whole block, which is taking the input from the step in counter, or also it is called as a step decoder. Also, it is taking input from the instruction decoder, external input, and condition. From all these places, this control signal generator take the input, perform the processing, and generate the control signal. Now we are moving to the next part, that is how it is going to generate the control signals. Now, first thing is that whenever it is going to generate the control signals, it will be first control signal is that whether it is related to the particular operations, that is a read write operations or memory read write operation. According to that, control signal will be generated. Whenever these signals generated, it will be a generate the individual control signal will be generated, and after execution of each instruction, of the end of each instruction, it is going to generate that signals, and which will be sent to the reset logic for the resetting the control steps in the step counter for to execute the next instruction. That is the working of the hardware control unit. Now we are going to see the how these hardware control units are designed, that we are going to see. All of you understand this block diagram of hardware control unit? Please put it in chat box. Okay. Now we are moving to the next part. We are going to see the design of hardware control unit. So hardware control unit is designed depending upon the four types of the approaches. First approach is sequential counter method. In this sequential counter method, it uses counters and timing circuits for the measuring the count, and counter is used for the measuring the count, and timing cycle is used for the how much time is required for the generating particular sequence. For that purposes, it uses counter and timing purposes, and that will be used for the designing the controller, and which will be a moderate the complexity of the circuit. So in this first method it will be done, which we are in next few slides we are going to see in details. Now second method is that delay element method. In a delay element method, it uses the clock for the as a delay element, which will be used for the mainly generating the sequence of the control signals. And third type, now state table method. In that, this state table method is traditional method, which is going to use the approach to sequential circuit design as well as the state table method representation. And last type is PLA, that is programmable logical array method. It uses programmable logic devices, that is a and or operations will be involved in this PLA devices, that is a related to the hardware control unit. Now whenever we are saying that hardware control units are uses the different approaches, or you can say that it will be used for the simplify the semantic method, using the semantic method through which we can design this type of hardware. Out of these first three, that is a sequential counter method, delay element method, and state table method. These methods are used for the small data values, which is we can see and observe, or it is having the less complexity of the data. But what happen whenever we are having huge number of data, that data cannot be handled by the human. In that case, we require this programmable array. In that, hardware control units are designed. That means in the traditional computers, these three methods are used, and nowadays VLSI technologies comes in existence. That from that point, it will be used as the programmable logic devices. Now we are going to see in detail. Next part, that is a we are going to see the first one is the sequential circuit through which, or sequential method through which we can see the how this the hardware control units are designed. Now, this is a typical flowchart which is mentioned in the circuit diagram we can use for the see the working of the processing unit. In that previous lecture itself, I have explained. First of all, any instructions comes in the processor, that will be stored in the instruction register. Then that instruction address, that particular instruction address will be stored in the program counter. What is the use of program counter? It will be holding the which next instructions which is we are going to execute it. That instruction address is stored in that program counter, which is mentioned in this circuit diagram as a PC. Now that program counter content will be moved to the memory address register. Whenever program counter content will be moved to the memory address register, means that instruction address is available on the address line. That is the meaning of this statement. Now next statement is that the memory address register, that is available in the memory itself, because memory consists of the instruction as well as the data. So it is mentioned that the M and in bracket MAR. So that memory address register, it consists of instruction and data. As I said that out of that data will move to the memory data register for the first instruction itself. After, whenever data is moved to the memory data register, that time program counter content will be incremented by 1. That when it is going to happen, when it is going to happen, it will be happen when the second instructions comes in the instruction register. That time program counter content will be incremented by 1. For example, in here is first instruction is there. Here program counter is having content stored in the particular memory location. For example, if I am saying that the 2000 memory location, first instruction is all data is stored, instruction as well as data. Now, after completion of the first instruction execution and data is moved to the memory data register, program counter content will be incremented by 1. That means initially it is in 2000 memory location. Now it will be moving to the 2001 memory location. After performing this task, we move to the next step. That is we want to move the data. Now, whenever we want to move the data, it will be in a memory data register. It will be moved to the instruction register for the execution. On data, we want to perform the operation, because whenever we want to perform any operations, we require two registers. One register name is source and another one is destination. So for that, at least two instructions. On that, we are going to perform the operation. After this data is available in the instruction register, then it will be decided which operations we need to perform. So instructions are having the 3 phases. First phase is fetching cycle. Second one is decoding cycle. And third one is execution cycle. Out of that, in the first instruction, whenever it is bring into the instruction register, it is a fetch cycle. Whenever instructions are decoded, that means it is a opcode will be find out and instructions start the executing. That is in a decode cycle. And execution cycle is nothing but the on data we are performing the processing. That time execution cycle comes in existence. So here in this box, f is equal to 0. That is a fetch cycle is equal to 0, which is mentioned here. And execution cycle is equal to 1. That means we are in an execution phase, not in a fetching phase. And after performing this execution phase, we go to the last stage. That is a execution cycle will be, if it require more time, it will be executed. Otherwise, it will be end. That is a operations which is we are performing here, which is also we can see the previous lecture diagram with the help of this flowchart. Now, next thing is that as we have going for the first method, that is a sequence of the or sequence counter or sequence state, which is mentioned maintain the hardware control unit. In that, mainly there are two parts are there. First one is we want to maintain the sequence number of the each execution process. Second thing is after maintaining the sequence, we need to use the counter for that particular method. So counter number is there. Now in this diagram, I have not explained, yes, what do you mean by S01, C01? that I am going to explain now. That is related to the sequence counter only. Sequence and counter both are mentioned in the form of the flow chart. That's why this method is called the sequence counter method. Here, first step is that we want to perform the execution. So we start the beginning. In the beginning only, external signal is given as a starting operations. So that is a state one. Sequence number one is that. What is our first sequence? Program counter content will be moved to the memory address register. That is our first sequence number. And in that time, we have to set the counter also. So C01, that is the sequence. In the sequence 1, counter 1 also going to send. Now, sequence 2, what is our operation? This is a sequence number. Okay, I will write the sequence number in this side. So, sequence number 2 is memory address register contents will be moved to the memory data register. That is the first operation. And second operation is that we need to increment the program counter. That is the program counter plus 1 is equal to next program counter value. Program counter content will be incremented by 1. And for this is the first step, counting first step. So that here it is written C02. And this will be a second step, that is a C03. Counting is 3. That is the third step. Okay, sequence number 2, second and third step is involved. Sequence number 1, only one counter is there. That is the only one step is involved. That's why I have said the only one counter value. You can give the any value to counter. Now here, sequence number 2, two sequence of instructions are executed. And that's why I put the counter value 2. That is C02 and C03. Now we move to the sequence number 3. In that, memory data registers contents will be moved to the instruction registers. That is a counter 4, which is we are going to set. Now, sequence number 4 is there. In that, again, two operations are there, but either one of the register is having value 1. So, for that, I put the counter value 05. That is if you are in a fetching phase, that time one value is there, that time execution phase is 0. This it is mentioned there. If phase cycle is having value 1, that time execution cycle is having value 1. Like that we can mention here. Now we move to the next sequence, that is the sequence number 5. That is the last sequence, that is the execution of cycle, that instruction cycle is executed. Like this we can maintain the sequence. We have to maintain the table of sequence and counter measure, which is involved in this diagram. Now here, first thing is we are writing the sequence number, and second thing is we are writing the counter number. So first sequence is, what is that sequence is there? S01, that is the sequence. In that only one counter is generated. That is I am writing here C01. Now sequence number 2, two steps are involved. That is S02. Two steps are there. That is first one is memory address register content will be moved to the memory data register. That is the first counter is going to set, that is a C02. And second, after that program counter content will be incremented by 1. That's I am setting the counter value. Next counter, that is a C03. Like this two counter we are setting. Like this we have to represent in a form of table. That is a nothing but we are using the sequence counter method. The first method which is I explain here. Any doubt here? Am I audible to all? Any doubt? Please put it in chat box. No doubt? Okay. Now, no doubt. Okay, no problem. Then we will move to the next part. As in the previous diagram itself, I have mentioned that the number of operations which is we perform on this diagram all is represented in a form of sequence number and counter. same operations, whatever theoretically I have explained, same it is mentioned in this next PPT in the form of the steps. First step is that as I mentioned here, identify the distinct phases in the flowchart. That means what are the different phases are there? We need to identify. That means we have to identify the what are the different operation. Each operation is separately that we have to first of all identify. For example, first operation which is I have mentioned that the uh, program counter content will be moved to the instruction address register. Then memory data register content will be moved to the instruction register like that we have mentioned. So for each operations we have considered as a different phase, and for each phase we have written this number, and in that sequence number of steps are there. For according to that steps we have given the counter value. Now second step is that identify the maximum number of sequential micro operation in each of these phase. Now we have identified the maximum number of sequential micro operations. That is for the first of all program counter content will be moved to the memory address register. Then the memory data register content will be moved to the instruction register. Then program counter content will be incremented. Like this, we have designed the separate micro operation. That is for each instructions. Total we have divided into the number of sub instructions, which is nothing but the sequential micro operations which is involved. So execute the k number of sequential operations with the help of the mod counter. That means we need to set the one counter for that, which is we have mentioned that in that previous PPT C0, 1, 2 up to 5, 6 that counter we are taken. So we have mentioned that. After that first step which we have done, that is the counter output can be decoded and used to generate the k control signals in a sequence to execute the k micro instruction. After that we are performing the after each counter output we have generated the execution step, that is a f is equal to 0 and k, e is equal to 1. That means it is a execution steps which is mentioned here, and that loop will be for the each instruction. That's why k number of instructions are there. So k number of time that loop will be continued, and at the end we have said the counter can be reset with and with the execute and fetch begin to set 1 and 0 respectively to start the new execution phase, which is mentioned here. For example, we go back here. After setting this, again we have to go to the this is for the single instruction execution process. Okay, after that we need to reset, and again we have to go like this. That is mentioned in the last step. That's it. Any doubt in this? Please put it in chat box. Any doubt in this steps? No. Okay, thank you. Now we are moving to the next part. That is the second method, delay element method, used for the hardware control unit. Now hardware control unit is based on the delay element, in that mainly phase cycle is involved. So whenever we are executing the any instructions, it is executed in a particular sequence only. Means for example, we will with the help of this flow chart we can see we start the beginning the operations. In that T0 is the timing required for the execution of that particular operation. T1, T2 up to T4 like this it is mentioned. Then C01 is nothing but the counter values are set. D1 is nothing but the D1, D2, D3, D4. These are the delay element in the each process which is required for the execution. Now, how we can perform these delay elements works in the hardware control logic, which is we can see for this delay element method implementation, there are 3 logics which is implemented for the hardware control logic, which we are going to see. Now, out of that, first one is that each sequence of the 2 successive micro operation required a delay element. For example, S1 and S2, these are the sequence of the micro operation. For example, in first micro operations, I'm using the whatever content in the program counter, that I am moving to the memory address register, MAR. That is the first sequence. Okay, and second sequence is that the you can say that the memory address register in that particular address register, whatever data is there, that will be moved to the memory data register. That means MAR, memory address register. This is nothing but the M. So whatever data is there, it will be moved to the memory data register. Whenever I am saying that the memory address register content will be moved to the, sorry, it is arrow should be like this. It will be moved to the memory address register. So that means the data, whatever instructions we are having, first instructions we are having, for example, in the address location 2000, instruction register is having that particular instruction is having address 2000 memory location. That memory location address moved to the memory address register. That means that address is available on the address lines. That is the sequence number 1. And sequence number 2 is content of that particular first instructions will be moved to the memory data register. That is the second sequence. So it in delay element, it says that the each sequence of 2 successive micro operations requires delay cycle. So first sequence is there, second sequence is there. In between that, this delay element is put. That is a before input. This first is there. After the first sequence, the delay element will be placed here, and after delay element output is connected to the second delay like here, which is mentioned here. So it will be here only. So it is mentioned with the help of this diagram. That is a hardware control unit implementation will be done like this. Means each micro operations in between the each micro operations delay element will be placed like this. Means here we can say that the here 2 micro operations are there. S1 is sequence number 1 and sequence number 2 of micro operation. In between that, this total circuit diagram of this delay element will be placed in between and it will be perform the task. That is the rule number 1. Now moving to the next rule, rule number 2. Again, in a rule number 2, it says that if you are having n number of lines are there in a flow chart. So input lines are there, and we need to take the common line from there. So we need to merge that particular line, and after merging, it will be given to the input to the OR gate that we need to perform here, which is mentioned here. So sequence number S1, S2, and S3. These are the 3 micro operations are there. In between 3 micro operations, delay elements are placed, and delay element output is given to the as an input to the OR gate, and that will be a merge here, and out from there control lines are generated that will be used for the hardware control unit design. So here it is rule is mentioned, n lines in a flow chart merge into the common lines are transfer into the input OR gate. That will be a second rule. Again we will see the second rule. Again one diagram is there. For example, if you are having the n number of input lines are there and only one output line is there. So n1 to n number of input lines are there and only one output line is there. That time that will be replaced into the n number of input lines into the given to the OR gate as an input 1 to n, and only one output line is generated. That means n lines in the flow chart merge into the common lines are transferred into the input OR gate, which is mentioned in this diagram. Now, rule is that whenever we are having the decision box in your flow chart, that can be implemented by the 2 AND gate. Now here, for example, is A is equal to 1. If S, go here. If not, you have to go here. Now, how this will be implemented in terms of the hardware? This is related, this flow chart is we are represented in a terms of the software, but in hardware, how it will be implemented? 2 AND gates are taken. One input of AND gate is shorted and another input is kept as a and another next gates and gates will be kept as a bar, and from there output is generated. One is for one output it is given as a yes and another one is no. So total this decision box in a flow chart will be replaced by the hardware using this two AND gates like this. These are the three rules which is used for the delay element. Any doubt in this? Second method, any doubt? Please put it in chat box. Student? No, okay. Thank you. We'll move to the next part, that is the third method. Now, sequential counter method. We move to the next part, that is a sequential counter method. In this sequential counter method, already we have studied the Booth's multiplication algorithm. All of you know that in previous unit, we have seen the Booth's multiplication algorithm. Same algorithm is represented here only. Flowchart of Booth's complement multiplication, which will be implemented for the sequential counter. So I have taken this same example. In that, first thing is that whenever we are using this sequential counter method, we need to divide the given problem statement into the number of phases. For example, this will be a initialization is a one phase in terms of the Booth's multiplication algorithm. Then after that, Booth's multiplication algorithm is second conditional phase is there, second phase, and last one is the third phase. Like this, it is divided. If you see these, some variables are different. Only one variable is different in terms of the Booth's multiplication algorithm. First of all, we start with the beginning. Then in that, the first phase, sequence number 1 is given. S1 is nothing but the sequence number 1. And then we have to set the number of counters for this. So I can set which sequence operations we are performing, C0, C1 and C2. Like this we have to mention. So first, what is the C0 operation? A register content will be 0. So A register is in Booth's multiplication and N bit register. So all number of bits we can set as a initially 0. That we have to perform. Then Q minus 1 we have to set as a 0. Next one is counter is equal to, you have to set as a n. N is nothing but the number of bits which is on which we are going to perform the operations. B is inverse. That is a in Booth's multiplication. B means we have taken as a m, that is a multiplicand. And Q is a multiplier. Sorry, B is multiplier and Q is multiplicand. Like this we have taken. Now again for that sequence number, next sequence number is given. That we have done in one phase. If you observe this, in that, what is your first step is that the first phase, or you can say that the first phase is that this will be a phase 1. Okay, phase 1 is there. So what are the control signals are generated here for this particular sequence? You can say that the C0, C2 and C3, these are the control lines which is we can generated or activated in the phase 1 whenever we are initializing the parameters of Booth's multiplication algorithm. Now, whenever we are moving to the second phase, in the second phase, here condition box is there, and here depending upon this condition box, we need to perform the two operations. Either we can perform the addition operation, subtraction operation, or directly arithmetic right shift operation, which is a common for the addition or subtraction operation. Arithmetic right shift operation is common. Now, if you move to the second phase, in that, in case of, you can say that the subtraction operation, for example, A is equal to this subtraction operations we are performing. In that case, it is going to activate the control signals like C6, C7 and C8. Why it is a 4 given? Because first thing is that we are setting the condition. We are checking the value Q0 and Q minus 1. Whenever Q Q0 is 1 and Q minus 1 is 0, that time first counter will be set, that is a C5 will be set. Okay, after that what operations we need to perform? A is equal to A minus B, so second counter will be set for that. After performing this operation, result is in a register, so A register content is there. So after that we are writing that A register contents and all these register contents as it is, that will be goes to the next step, that is a arithmetic operations phase. So like this 4 counter will be set, means for a value, taking the value of A register, B register, then condition of Q0 and Q minus 1, and after that result in a register only. Like this 4 register, we required a 4 control signals to generate here. Now if you are taking the addition operation of the particular number, in that first counter is which is required, that is a counter value Q0 and Q minus is having value 0 and 1, then we can perform the addition operation, that is A is equal to A plus B. In that first value A register contents will be required 1 counter, B register will be required another counter, and A plus B operation is equal to A, that will be required a next counter. So 3 counters are required. So in this page we can say that the if you are performing the subtraction operation, then control signals are C5, C6, C7 and C8. These control signals are generated. If you go for the addition operations, it is going to generate the control signals C6, C7 and C8. These control signals are generated. But yet we are not completed the phase 2. Now we move to the next part. In the second phase itself, it is written that the arithmetic shift, right shift operation of register A, Q and Q minus 1, as well as counter should be decremented by 1. These are mentioned. For that, again the counter values are set C1 and C4. So these many control signals are generated in a second phase if you consider the Booth's multiplication algorithm if you want to implement in a hardware control unit. So how many controllers are generated? In case of subtraction, 4 control signals are generated. In case of addition, 3 control signals are generated. And again, these either you go for the addition or subtraction operation, or if you are having the values of Q0 and Q minus 1 is 0, 0 and 1, 1, that time also we have to go to the compulsory steps, that is a arithmetic right shift operation of register A, Q and Q minus 1. So C1 and C4, these are the control signals are compulsory generated out of this addition and subtraction operation. That is that many number of signals are generated in the phase 2. Now third phase, whenever we are enter into the third phase, in that it is going to check the first of all counter. If counter is not 0, this loop will be continued. So second phase is repeated n number of times. So if this phase is repeated n number of times, these control signals are generated for the phase 2. That means phase 2 is very important as an implementation point of view. We have to give a more focus on that. Now, next, if is not equal to 0, we have to generate the final result. Whenever we are generating in Booth's multiplication algorithm, we are generating the final result that contains of the register of A register and Q register is the final result. So content of A register move to the out bus and content of Q register again move to the Q out bus. That means that is a out bus is nothing but the output which is we want to display, and in bus is nothing but the input given to that particular register. That's it. So for that also we need to set the counter, that is the last phase. So A register, whenever you are moving to the out bus, that time C9 control signal is generated, and whenever you are moving content of Q register to the out bus, that time counter control signal C10 is going to generated. And after performing phase 3, we will end that particular operation. If counter is equal to 0, then only we can perform the end operation. That will be a sequence counter method. All of you understand this? I will explain with the help of Booth's multiplication algorithm also, which is also I have put it in the PPT. Any doubt? No? Okay. Now we are moving to the same diagram is there, but I compare with the Booth's flowchart, algorithm flowchart, multiplication algorithm flowchart. Here, if you observe that it will be a start or begin, both words can be used for the designing the flowchart. So no problem. Here, A register is 0, Q minus 1 is 0. Here, A register is 0, Q minus 1 is 0. Then multiplicand and multiplier is not mentioned here in this, but here B register is mentioned and Q register is there. So Q register means multiplier, Q register means multiplier, and M register is nothing but the B register, that is a multiplicand, you can say that. Only that alphabet difference is there. Now counter is equal to N is given here. Again here counter is equal to N. So first phase of the Booth's multiplication algorithm and in the represented in the flow chart, which is I have explained now, which is set. Now we are moving to the next part, that is the conditional blocks of the content of register Q0 and Q minus 1. Depending upon the value of the registers Q0 and Q minus 1, we need to perform some certain operations. If you are having the Q0 and Q minus 1, both are having value either 1, 1 or 0, 0, directly we need to perform arithmetic right shift operation of register A, Q, Q minus 1, and then we need to decrement the counter value by 1. If not, that means Q0 and Q minus is having value 0, 1. That time we can perform the addition operation of register A is equal to A plus M, and then go to the next operation, that is the arithmetic right shift operation of register A, Q, Q minus 1, and counter should be decremented by 1. If not, means that is Q0 and Q minus is having value 1, 0. That time we can perform the subtraction operations. A is equal to A minus M, and then arithmetic right shift operation of register A, Q and Q minus 1, and then decrement the counter. Like these operations which is involved in the second phase of Booth's multiplication, same will be represented here. The only difference is that in that algorithm, we have not written the sequence number as well as the control signal numbers. C1, C2, C3, C4 like this, that is a control signal number, and S0, S1, S2, S3 like this, which is mentioned that will be a sequence number of operations which is we are going to perform. That is we are dividing one instruction into those sub micro instructions. That's why. Now third phase is that whenever counter is equal to S, it is saying that the end of operation. But in a Booth's multiplication algorithm, A register, content of A register and content of Q register indicate the operation or a final result of the Booth's multiplication. Now here counter is S. In that time counter is equal to 0. Yes, this condition is satisfied. So A content, register of A contents register will be displayed on the output device, as well as Q register contents will be displayed on the output device. That is the third phase, which is I explained with the help of the comparative between these two algorithms, which is similar. Only difference is that we have put the sequence number and control signal number, and the algorithm is divided into the number of phases whenever we want to design the hardwired control unit. All of you understand this? Any doubt? Any doubt? Student, any doubt? No? Okay, now we will move to the next part. For example, if you want to perform some certain operation with the help of the example also, Booth's multiplication, this will be a flowchart, and this flowchart is converted into the numerical problem which we want to solve. For example, 5 multiplied by 4, which is already we have solved. So first phase is that the initialization phase of the register A, Q, M and counter. So A register, Q minus 1. Q minus 1 is also here. What is the multiplicand and what is the multiplier? Multiplicand is M, multiplier is Q, which is mentioned in the phase 1 itself in the problem statement. Now, next thing is that we have to go to the next phase, which we have to perform. That will be a second phase. That is a from the second condition box to the all the arithmetic right shift operations. In that, either you directly go, if you are having the q0 and q minus 1 is having value 1 1 and 0 0, that time arithmetic right shift operations, which is we had done here. If not, if it is having value 1 0, then we are performing the subtraction operation, which is done here. If you are having addition, that means q0 and q minus 1 is having value 0 1, so that we are performing the addition operation, which is also done here. So that is a and arithmetic right shift operation also we are done simultaneously in the second step itself, whenever it is having the subtraction or addition operation. That is comes under the phase 2. So this will be a phase 2, which is we have completed in terms of the whenever we are solving the problem. Now last stage is end of operation. So whenever we are ending the operation, it indicates that the content of this register A and Q represent the final result. So A and Q register represent the final result. Like this, if you map the software with the hardware implementation, we can do like that. That will be done in a sequence counter method. To sequentially, we have to implement that particular hardware. Now we move to the next or last part, that is with the help of the programmable logic method, we can implement the hardware control unit. As we have seen that the control unit design method, various method which is we have discussed, that is a sequential counter method, delay element method is there, which is we have discussed previously, which is taking the small control unit due to their size and complexity. So we need to increase their size. In the modern computer systems, which is uses the VLSI technology, that is a very large scale integrated technology, which is based on the circuitry used for the designing the control units. So it will be used for the designing the control unit. For such one structure is used, that is a PLA, that is a programmable logic array. That programmable logic array consists of array AND gates followed by the OR gate. So we are going to see the working of this block diagram of PLA, that is the programmable logic array. Here AND and OR both are programmed to implement the combinational logic functional of several variables, which is used for the implementation purpose. Now here we are having the n number of input, that is x1 to xn. These are the input which is given to the input buffer and inverter, and then from there it will be given to the AND array. From AND array output will be given to the OR array, and OR array output is generated, it will be given to the output buffer. Like this block diagram is generated for the PLA devices, which is used for the huge size of data as well as the complex circuit design. So same block diagram will be represented here. Input buffer and inverter will be represented here. NOT gate with the NOT gate, input buffer here. Then here AND gate is n number of inputs are there, AND gate, and output of AND gate is connected to the input to the OR gate, like here, and then output is generated, that is output buffer directly it is given here. Like this PLA logic is implemented for the hardware control unit. Now in this lecture, any doubt? This is related to the hardware control unit. Again, this will be a PLA, how it will be implemented, same block diagram is there. Any doubt in this hardware control unit? No. Any questions on this? These are all theoretical, but too many diagrams are there. Please put it in chat box if you are having any doubts. No. No doubts. Okay, then in next lecture, I will explain the next part, that is a microprogram control unit, and difference between the, what is the difference between hardware control unit and microprogram control unit, that I will explain. Now we have studied the hardware control unit. In next lecture, I will explain the microprogram control unit and difference between the hardware and microprogram control unit. You can study and come for the next lecture. Okay. Having any doubt? Shall I end this session? Yes, okay. Thank you.